As an aircraft cruises, friction with air and atmospheric particles generates a significant buildup of static electricity.
This electrical charge is caused by the rubbing of the airframe against rain, ice, and dust particles.
While some energy naturally bleeds away, the charging rate often exceeds the rate of atmospheric dissipation.
Consequently, the accumulation intensifies, creating a potent electric field surrounding the entire exterior of the vessel. This static energy doesn't spread evenly. It tends to migrate toward the sharpest points of the fuselage. High concentrations form at the tips of the wings, the nose, and the edges of the tail. As voltage climbs, the surrounding air molecules begin to ionize, preparing a path for a sudden release. Once the air becomes conductive, a rapid energy burst occurs, known scientifically as a corona discharge. These bursts manifest as miniature lightning bolts, jumping from the airframe into the dark, surrounding atmosphere.
While visually striking, these uncontrolled discharges present a major threat to the plane's sensitive electronic systems.
Modern avionics are constantly exchanging data with ground stations, GPS satellites, and other aircraft in the vicinity.
A sudden corona discharge produces massive radio frequency noise that can mask these essential incoming electronic signals.
To combat this, jet engines divert hot bleed air through internal ducting to heat the wing's surface.
On smaller turboprop planes, flexible pneumatic boots inflate and deflate to physically crack and shed ice layers.
Electrothermal heaters are also used on windshields and pitot probes to maintain visibility and accurate flight data.
These sophisticated sensors and heating elements work in tandem to ensure safe operation through the harshest winter conditions.
Jet fuel is primarily stored inside the hollow wings, acting as a structural weight to balance aerodynamic lift.
Computer-controlled pumps manage the flow between tanks, maintaining the aircraft's center of gravity throughout the long flight.
In emergencies, high-volume jettison valves can rapidly dump fuel from the wingtips to reach a safe landing weight.
Fire detection loops monitor critical zones, using thermal sensors to alert the cockpit of any localized heat spikes.
If a fire is detected, high-pressure halon bottles discharge a chemical cloud to instantly suffocate flames within the engine.
Nitrogen inerting systems replace oxygen in the fuel tanks with non-combustible gas to prevent any internal ignition. These layers of containment and suppression ensure that fuel remains a safe energy source, even in extreme conditions.
Hydraulics act as the aircraft's muscles, using high-pressure fluid to move heavy flight control surfaces.
3 independent systems operate at 3,000 psi, ensuring full control even if one system fails.
Fly-by-wire computers translate pilot inputs into precise digital commands for the hydraulic actuators. Pistons made of high-strength titanium extend and retract to deploy the massive landing gear and flaps. Servo valves regulate the flow of fire-resistant hydraulic fluid with microscopic precision during every maneuver.
If total power is lost, a ram air turbine deploys to provide emergency hydraulic and electrical energy.
At high altitudes, the thin atmosphere requires the cabin to be artificially pressurized for passenger survival.
Hot air from the engine compressors is cooled and conditioned by air cycle machines, known as packs. The outflow valve acts as a precision vent, constantly regulating internal pressure by releasing excess air.
If pressure is lost, emergency oxygen masks drop automatically, triggered by chemical generators or high-pressure cylinders. Integrated sensors maintain a precise balance of temperature and humidity to ensure comfort in the freezing stratosphere. Heavy structural seals and reinforced windows keep the internal atmosphere contained against the crushing external vacuum.
This life support network allows thousands of travelers to fly comfortably in the most hostile environments on Earth.
The landing gear must withstand massive impact forces while providing a stable platform for ground maneuvers. Massive oleo struts use a combination of compressed nitrogen and hydraulic oil to absorb the energy of touchdown. High-torque electric or hydraulic motors drive the steering actuators, allowing the nose wheel to pivot with precision.
Carbon ceramic brake discs utilize intense friction to convert the aircraft's kinetic energy into heat during high-speed landings.
Anti-skid systems monitor wheel rotation, automatically pulsing the brakes to prevent dangerous tire blowouts on wet runways.
Thermal fuse plugs are designed to melt and deflate tires safely if the brakes reach critical temperatures after stopping.
This robust mechanical assembly ensures a smooth transition from the high-speed sky to the safety of the Earth.